So I'd like to say thank you to the conference organizing committee for inviting me to speak today. I'm really thrilled to be here and excited to be back at SciPy after several years away. I think my first SciPy was around 2006, and I think the last time I came was really around 2016 or 2017. So I'm really happy to be here. Now, astronomy folk have been regular attendees at SciPy for quite a long time. So some of this might sound familiar to you, but my hope is to give you a little bit of history in addition to some of the science and engineering. And I encourage you to liberally seek out space geeks that are in the crowd this week. There's a bunch of folks here with a wide range of interests and experience, and it's really fun to talk to them. With that, let's talk a little bit about astronomy. So astronomers use a wide range of telescopes that operate over the full electromagnetic spectrum. And pictured here are just some of the large space missions and ground-based observatories that we use to collect data over a large range of wavelengths. And these facilities often work together to enable science that benefits from multiple observations, or those that need to occur over very short or very long time frames. Some telescopes even share the time allocation process to facilitate this. Additionally, astronomers often need precursor or follow-up or time-dependent data in order to extend and enhance the scientific studies that they're doing. And one result of this is that we've been growing large archives of data for decades now. So at Space Telescope, we run MAST, which is the Mikulski Archive for Space Telescope. It's named after our former senator, Barbara Mikulski, who's a real firecracker and who's been a staunch supporter of both Hubble and James Webb for decades now. MAST itself is focused on UV, optical, and IR data sets from over a dozen missions. And we do contain a large amount of data, some of which is also from ground-based observatories, such as Pan-STARRS. But today I'm going to focus on the telescopes where we're involved in major mission operations. Those are primarily the Hubble Space Telescope, the Webb, and the Nancy Grace Roman Space Telescope, which is due to be launched in the future. So as you might have already guessed, data-driven astronomy, supported by data science, is becoming increasingly important because of the large volumes of data that are now being created and that are accessible to the community. The Hubble Data Archive itself is already an amazing resource of information. It contains more than just images like the ones you see here. We also have large databases of photometry, spectroscopy, and other high-level extracted information that we make available to the community. So let's focus now on those three big missions and what's involved to support them. Large community missions often require complex software to support observation planning and data processing, as well as science collaboration, analysis, and archive needs for the mission and community. And this results in a large collection of software and tool sets that include things that help astronomers plan their observations and make effective use of telescope time that's available, pipelines that focus on instrumental calibration, removing unwanted electronic signatures and noise, including things in space that are not coming from your objects of interest, like cosmic rays, as well as large combination object identification and class functionality. We use data simulators to explore the parameter space of observations and instrumentation, data reduction strategies, to create data sets that aid in machine learning and training and testing, as well as post-processing tools for visualization, image combination, access to large archives of data, and to mine that data for new or interesting characteristics. The majority of these tools now use Python as their primary. However, in the beginning, there was no Python. And this was complicated by the fact that long-term large missions usually evolve slowly but on many fronts, and small missions and research teams don't often have the funding or long-term membership to support developing or maintaining new software. And so what does this system evolution really look like? Hubble started off with code written in Fortran, specifically for its first spectrograph, and the rest of the software used to calibrate the onboard instruments was developed in a combination of Fortran and the IRAF specific language, SPP. IRAF itself is really an astronomy-specific platform in its own right. It was developed in the late 70s and early 80s, around the same time that the FITS data standard was created. And it became a catch-all environment that was used by most, if not all, observational astronomers, and some of them are still using it today in different forms. FITS itself was designed specifically for astronomical data and includes provisions for describing photometric and spatial calibration information. But as you can see, we don't even start FITS. We started with GWC. I'm not going to go into GWC. These data formats and software have existed over a range of operating systems and hardware, and we need to support users running on those and other platforms as well. So Python's adoption in astronomy is in no small part due to the efforts of these two, Perry Greenfield, and he's here, and you should go find him and get cool stories from him, and Rick White, who's not here, but he still works at the Institute and contributes a lot to MAST itself. They had a desire to help astronomers move to a language with broader use and support from the greater software community, to help them as well as help the developers supporting the software that they used. So astronomy already had this large amount of software and tools in astronomy-specific languages, and eventually they settled on trying to move the community to a different software interface based on Python, and as a compromise created the PyRAF command line system. This allowed astronomers to access the tools that they were used to using in IRAF while helping them start migrate towards Python. Once they discovered the real power that Python presented, we ended up supporting a large part of the original IRAF system in PyRAF as well as standalone Python tools. And this was greatly facilitated by the collaboration between John Hunter and Matt Plotlib, developers at Space Telescope, which gave us access to powerful plotting capabilities that were GUI agnostic, that were supported across platforms, and able to produce publication quality plots, rather effectively competing with IDL and pgplot and SuperMongo. And as part of this move to PyRAF, they really needed to develop better ways to support the FITS file format that astronomers use, while efficiently supporting the typically large arrays of data and structured data that Hubble processing in particular needed to be able to handle. And so NumArray was written to address these issues and support our processing needs. And while it was efficient for large arrays and compatible with numeric, it really was not fast enough for the small arrays, and the existence of both these packages divided the Python community. And so Travis Oliphant then refactored and combined the best parts of numeric NumArray, creating NumPy, which is now a foundational library for scientific analysis, and along with the scientific Python ecosystem, has become the backbone for astronomical software. So Python, though initially used as a scripting tool by the community, now, with more tools and libraries that meet its workflow needs, is widely adopted. And this is in part due to the fact that Python is concise and easy to read and understand and teach, which made making software faster to implement and maintain. It's usable for light workflows and primary implementations. It offers a broad array of libraries and supporting tools. It's extensible and can interface with other commonly used languages. And it has well-maintained testing and distribution options. Additionally, it's portable and well supported by a large community. And so the open source Python community is having a positive effect on the way astronomers interact with their data and software while making it easier to support them. So let's talk a little bit about the software community and collaboration. Okay. By 2011, there was growing support to create an astronomical software library that would help unify the disparate set of tools that existed in the wild, often with overlapping functionality, while fostering a shared astronomical ecosystem that would help astronomers, teams, and missions achieve their goals. And so the AstroPy collaboration was born. And AstroPy itself is driven by open development and decision-making and committed to fostering an inclusive community. It has a large number of satellite-affiliated and coordinated packages that help extend the core library. And while it's focused on supporting professional astronomers, much of the functionality it provides is useful across scientific fields. And so AstroPy itself is being used to support major astronomical missions, and those missions contribute developer time to support the project. The science calibration pipelines are a big part of this. They supply important mission needs for the data and detector processing, and they take the raw telescope data and transform it into science-ready products. For Hubble, the majority of the core software is written in C, which has evolved over decades of time. The exception to this is the cosmic origin spectrograph, which is installed during the 2009 servicing mission, and it's written in Python. Because Hubble has this wide range of UV optical and near IR detectors, it also has a lot of differing calibration needs, which often drives the design of the software. And so, even though the code is available in GitHub, there are a few astronomers that contribute to its maintenance and augmentation. This is in part because the code is complex, it's difficult to understand. But also, each instrument is its own beast, with out-of-sync software updates and unique processing needs. In contrast, the majority of the web software is written in Python with C extensions. The instruments share common core code, but this code is further complicated by the large number of observing modes that web has to offer. But they do make extensive use of the AstroPy ecosystem, and astronomers, by and large, can understand and contribute to its direct testing and maintenance. This common shared understanding of the code gives them greater confidence in the results and the ability to focus more on the software that they need to create in order to do their science. So two of the other important packages for us are GWCS and Asdiff. Asdiff provides us with a really nice way of saving the metadata that describes the observations, along with the detector data. And I'm going to let Perry talk to you more about Asdiff. He's giving a talk later this morning, so go check him out. The FITS format itself made it difficult to handle the complex needs of modern astronomical data sets, especially the world coordinate systems that we use to describe where the telescope is pointed. And so we created the GWCS package to manage the complex sets of models that we use to describe how light from objects we're observing gets translated into extremely precise precisions on the detectors and vice versa. So GWCS, the Generalized World Coordinate System, is supported by AstroPy modeling, and it allows you to string together mathematical models to translate coordinates between two or more different systems. And we use this to translate perfect sky coordinates to detector coordinates and intermediate systems as well, because sometimes there are effects that happen that make sense to correct for in different coordinate reference frames. The combination of GWCS and Asdiff makes it possible to save these sometimes complex analytical models into the data itself. And when the data is reopened by the user, they're automatically transformed into Python objects that are ready for use. So another of these coordinated packages that gives astronomers command line access to these large archives of data is Astroquery. Astroquery can be used to search for and return information on data sets that exist in a wide variety of astronomical archives. And the MAST submodule can be used to search for mission data that we support, whether it's stored in the cloud or on premises at the Institute. So I've talked now about some of the major software and data needs. Let's look at how volume affects this equation. After 32 years in operations, we've collected a little less than 200 terabytes of data in the Hubble archive. It's processed and reprocessed several times a year for the instruments that are currently active on board the telescope. And that data is also synchronized at archive centers in Europe and Canada. Webb is expected to generate about 114 terabytes of science data each year. And over its 5-year mission, we expect around 650 terabytes. However, the launch was so good, and the telescope is operating so well, that we expect it to operate much longer than that, so that number is going to go up quite a bit. Now, in contrast, the Nancy Grace Roman telescope is expecting to generate about 9 terabytes per day. That's almost the same amount of data that we get from Hubble in a year. In the first 5 years of its mission, we expect to have 20 petabytes of data in the archive. And that's the primary archive. That doesn't include backups of all the data. Because of this large amount, we've decided to split the archive between on-premises storage and cloud storage, as well as provide a data local analysis environment in the cloud that's going to be open to the community. And so science platforms at Space Telescope are being designed with influence by the research and data science communities to support machine learning and custom data reduction and analysis. We're using flexible, scalable architectures, and we have high throughput access to the data that's also archived in the cloud, and scalable resources that allow science needs and technology to evolve. So JWST is currently using our development platform for training and tutorials, and Roman will provide a fully fledged analysis platform as part of its mission. Hubble data itself from the currently active instruments is being reprocessed in the cloud and made almost immediately available through the Amazon Open Data Sponsorship Program. And if you don't know about this, the ODSP makes public data available in S3 buckets with free access and free download to the public. And you can search and retrieve this data, this Hubble data, through the astroquery.mast module. And that's regardless of whether you're looking for data that's in the cloud or on premises. Hubble reprocessing is also using machine learning in order to predict cloud resource needs for specific data sets. And one of the developers who spent a lot of time working on this is in the audience today. And if you want to learn more about that, you should definitely go talk to Rue. So let's look to the future a little bit. You've heard me mention Roman a few times now, but I haven't told you much about the mission itself. The Nancy Grace Roman Space Telescope is due to launch in the mid-2020s and be complementary to other missions then currently in operation, such as Euclid, one of the European-based missions, JWST, and the ground-based Rubin Observatory. It's also going to be launched on a rocket. It has a small complement of instruments, which include the WFI, that has an array of near-infrared filters, along with a GRISM and PRISM for spectroscopy. It has a primary mirror that's roughly the same size as Hubble, but around 100 times larger field of view. I'm going to run this animation here, which gives you a good visual comparison for what that really means in terms of the data that we take. What you're going to see here is a single exposure, the size of a single exposure. So Roman is due to be launched in orbit at the Sun-Earth L2, the same as Webb. And it has two primary instruments, the WFI, which has 18 4K by 4K detectors. Each of these is twice the size of a JWST detector, and there are nearly twice as many of them. And each time we take an exposure, we're going to record data from all of these detectors. There's also going to be a chronographic imager, which is being flown as a technology demonstration, and this means that it's not expected to be used over the full mission time frame, and it has to meet less stringent requirements in order to achieve the mission success. Now, since Roman is primarily a survey telescope, It has pre-selected mission surveys, and it's focused on measuring dark energy, investigating exoplanets, and great observatory astrophysics. It's also going to dedicate about 25% of the time to a competed general observer science program. So Roman is also breaking the mold and operating with a shared ground system, with multiple institutions providing commanding and software and data processing in order to meet the Roman mission objectives. This requires a great deal of coordination and understanding of each other's operational systems, the procedures we follow, the development schedules, and connecting pathways. And it's heavily related to the science calibration pipelines that I talked about earlier. Space Telescope and IPAC in California will be collaborating to produce science-ready products for the community, where SDSCI will create all of the detector calibrated data for the WFI exposures, and IPAC will do the higher-level processing for data coming from the exoplanet survey and in the spectroscopic data sets. We'll be exchanging those data sets through a multi-center cloud presence, and then providing them back to the community using a combination of on-premises and cloud data availability. Now, all of this, we hope, is going to help facilitate supporting the open science that NASA is interested in. Unlike other telescopes, all Roman data will be non-proprietary and come with no exclusive access limitations. We expect the easy horizontal and vertical scaling in the Roman science platform environments to allow for intensive processing and large images and complex scientific analysis workflows. And additionally, we plan to have open development and community software support for science calibration processing, visualization tools, and libraries that facilitate recalibration and post-calibration of data analysis by the community. So because of this large, upcoming, and rich data sets, the Data Science Mission Office, in conjunction with astronomers and developers in MAST, have recently created Hello Universe, which is designed to help astronomers develop machine learning methods for astronomical discovery. And it provides this by making high-level science products available that are appropriate for testing and benchmarking new machine learning algorithms, along with instructional Jupyter notebooks that provide step-by-step examples of how to apply machine learning to the data. These accessible data sets, along with the available software, will help provide a better understanding of systematics between missions and large surveys, while helping to connect observations to the underlying physics. And we hope that shared calibration processing and data models for science products may help normalize data software standards in the greater astronomical community and with our partners. And mission tools that take as input standard data models and produce standard data models are easier to share and build community tools against. They promote the adoption of common software frameworks to interact with that data. And they maximize the sharing of software, which may improve work for future missions. And Python has been a very large part of facilitating all of this. And so, finally, I'd like to leave you with this. Launching space telescopes is really stressful. I can describe my personal stress as equal parts terror and excitement. But when people and the hardware and the software all come together and work, you get images like this that capture the amazing universe in which we live. Thank you.
That's great. We have some questions on Slack. Let me see. Start with Logan, who asked two parts. What has been the most useful scientific Python package for supporting the work you've done? One. And then if you were a magician, you had a magic wand, and you would wish to make a request, what request of the Python scientific stack would you make?
Wow, those are two really good questions. I think I'm going to have to put some thought into the second one. Maybe I'm going to answer that one on Slack. That's really good. The first one, I think AstroPy has been really the best package for us. It really supports a lot of our science calibration, a lot of our user tools, and a large part of the community at the same time. And it allows us to share the software and the tools that we use with a large variety of people.
Benjamin is saying, are there any plans to open up the web data in a similar ways to the plans for the Roman data?
Yeah, by open, so Webb does have proprietary data, so there are science teams that propose to get time and money to reduce the data. Once they've done that, that data becomes public as well, but there are also lots of immediately public data sets. We are talking about making those data sets available through the Amazon Open Data Science program, like we do for Hubble. So they may be available both on the web, in the cloud, and from the Institute directly. But currently, all of the James Webb Telescope data is stored on premises at Space Telescope, and it's easy to access.
Question from Max, who says, great talk. Max asks, is SDSci working on any open source Python tools for managing telescope scheduling, like time domain astronomy or targets of opportunity? Can you explain what those things are?
Time domain astronomy is really focused at objects that require information that's taken over either a very long or very short time frame. So supernovas, finding supernovas that go off would be part of time domain astronomy. Looking for exoplanets to some extent is also time domain astronomy. What was the other part of that?
The targets.
Targets of opportunity. So targets of opportunity are things that astronomers have said, oh my gosh, we really want to observe this. We don't know when it's going to be available or if this event is going to happen, like a supernova going off. And so when they go through the time allocation process, the committee says, okay, we think this is cool. You may get to observe this. If it happens, we'll stop what the telescope's doing. We'll go point to your target of opportunity. We'll take the data, and then you'll get it. So that's what target of opportunity is. The planning and scheduling system uses both Python and Java, JavaScript, and a few other things. There aren't very many of their tools that are available in the open source community, but I know that there are a lot of astronomers who are part of the open source community that do contribute tools to help with that.
Sounds hard. John asks, what are the top 3 ways this data will benefit society?
Oh my gosh.
You can do one. Maybe you can do one.
The top 3 ways. The amount of oohs and ahs will increase substantially, right? I think one of the coolest things is that we expect a lot from JWST, but we also don't know what to expect at all. It's so sensitive. It's operating in space in wavelengths that we don't have a lot of modern high-resolution data for, or that are impossible to get from the ground. And so I think some of the ways it'll affect us are still yet to be discovered.
Great. From Jessica, will the Roman data be available in the cloud as well? And how is the mission facilitating compute infrastructure / environment?
So the Roman data, different from some of the other astronomy missions, is all available immediately. As soon as it's taken, it's available. It doesn't matter who's proposed or what you're doing. It's all right there. We are supplying all of the calibrated data. So once we've done the detector calibration, all of that data gets pushed up to the cloud and we continue our analysis, and it's available through Amazon. We are also providing low level, so the pre-detector calibration data is freely available, but we're storing it on site because that facilitates the reprocessing that we have to do, and it's expensive to pull data in and out of the cloud. So for that reason, that lower level data stays on-prem. But if there are large science teams that may want to work with it, it's possible that we could push it into a cloud repository for them to access as well.
Very serious question from Paul Ivanov. Is it a coincidence that the Roman field of view is the shape of a space invader?
It's not a coincidence, but it's a very happy accident, and I support that. It's in that shape of field of view. The shape of that is because of the large number of detectors, the size of the optical field of view, and the fact that the detectors, in order to fit the electronics on board for all of the detectors in the package, they have to be rotated and moved in a specific way.
Oh, that was a much more interesting answer than Paul's snarky comment. Question from Tyler. Has SpaceX been involved in any of this work?
SpaceX has not been involved in any of this work yet.
Okay. Question from George. Are there interesting problems associated with use of community source software for mission operations in terms of mission safety, integrity, or is actual mission operations distinct?
So mission operations is mostly distinct. In terms of open source software, we definitely don't just accept all pull requests from the community, right? So if there are, sorry, let me get some water. If there are improvements that can be made, especially to the science calibration parts of the software, astronomers can create pull requests, and they'll get reviewed. They'll be discussed among the calibration teams that help us run and understand the detectors and the instruments. And if they're approved, they'll get added into the pipeline. Now that pipeline gets pushed to our back-end systems, which are regularly running and processing the data.
All right, we're at time here. I'm going to take the privilege of asking the last question. So I heard that James Webb had JavaScript running on it.
It does.
Do you have a secret agenda to get Python onto the Roman telescope?
Oh, I wish. I wish there was a secret agenda. But we're actually not writing the instrument control software. So on James Webb, JavaScript does run the instrument control on board the telescope. There was a study done a long time ago that decided, what would be the best language to use, and JavaScript was chosen. It's like an old forked version of JavaScript, but that's there. There is no Python on board Roman itself, although Python is being used on some other space instrumentation, like the Mars rover, I believe, maybe a Mars lander. For Roman, we're not developing the scripts. That's being done by Goddard Spaceflight, and they're not using Python.
Too bad. All right. Thanks, Megan.
Yeah,
that was great.
thank you.
Thanks, everyone. We're going to have a 15-minute break, and then the SciPy tools at 10 o'clock. Thanks.